All right. So here's the quotient rule. I'm just going to start off by having you write it down. The blue box is the Leibniz notation version. And down here we kind of have prime notation, which is a little easier to look at. So if you are taking the derivative of the quotient of two functions, f divided by g, the way you do that is gf prime minus fg prime divided by g squared. So that's just the regular function g quantity squared. It's kind of a nasty rule to use. I mean, it's just messy. It's not super difficult to use. But in normal circumstances, in normal years, you would have to memorize this rule. And there's a little mnemonic device that people use to memorize this rule, which is, since we have a fraction, I'll consider g to be the low part of that fraction. I'll consider f to be the high part of that fraction. And there's a little rhyme that goes, low d high minus high d low square the bottom and away we go. So low d high minus high d low square the bottom still referring to g, and away we go. And it's very dumb, but it works. Because if you try and say it the other way, like with the wrong order in the numerator, it won't rhyme, right? So if you were to go high d low minus low d high, square the bottom and away we go, that doesn't rhyme. So low d high minus high d low, square the bottom and away we go. And the d just means, right, derivative of. All right, give me a green check when you are good with this page. Show you the proof. It's kind of gross. So let's just focus up here. I let capital F of x just be the quotient of lowercase f and g. And so what I'm doing here is then capital F prime is just my limit definition of derivative, right? And now I'm transferring that limit definition to the right-hand side. So I'm replacing capital F of x plus h with lowercase f of x plus h divided by lowercase g of x plus h minus f of x over g of x over h. So we can simplify this by getting a common denominator, which is g times g of x. So making both of those have that common denominator, combining them into a single fraction, and then I'll put the h over 1, I'll flip it and multiply, and I'll end up with here. So that's just a bunch of algebra. All right, so I have this situation. I'm now going to add and subtract f of x times g of x. So here I've added and subtracting the same thing. So I'm not substantially changing anything. I'm just adding and subtracting the same thing. So I'm really adding 0. And up here in the denominator, or sorry, in the bottom. All right, we can then split that out into two separate fractions in my numerator. Putting h under both. And so now we start to sort of recognize what's going on here. What is this little factor the definition of in the chat? When I take the limit as h approaches 0, what is that going to become? Not G prime, F prime, right? Good, that's F prime. So then we have G times F prime. What about this guy? What's this going to become? That's G prime. And then when I let H go to 0, this just becomes G of X times G of X, which is G of X quantity squared. And thus we've proven our rule here, right? So I like to walk you through the proofs. This one's like so algebra heavy, and it would take like 10 minutes to get through that I mean, you've seen enough of these now. So now we've proven the rule, we can use it. Let's go ahead and use it. All right, here we have y equals the quotient x squared plus x minus 2 over x cubed plus 6. So this is where it becomes useful to start using your derivative operator so that you can kind of keep things organized and you don't have to do things all in a single step. Because you'll get confused and you'll start making clerical errors. So here's what I mean by that. Let's set this up to take the derivative, but I'm not going to take the derivative all at once. I'm going to use my quotient rule. And I'm going to go low, d high. All right, well, low is x cubed plus 6. And then d high. So I'm going to say d dx. So take the derivative of the numerator, which is x squared plus x minus 2. All right, and that tells me I'm about to take the derivative of that x squared plus x minus 2. I just haven't actually done it yet. All right, minus high, which is x squared plus x minus 2, d low, so times the derivative of the denominator, x cubed plus 6. So again, I'm setting it up. I'm saying I'm about to take the derivative of x cubed plus 6. I just have not done that yet. Square the bottom, so square x cubed plus 6, quantity squared, and away we go. Great. So now we're all set. We can see where we need to do calculus, here and here. We just haven't actually done it yet, so now let's just take that step and do the calculus on those parts. So I'll have x cubed plus 6. The derivative of x squared plus x minus 2 will be 2x plus 1 minus x squared plus x minus 2. The derivative of x cubed plus 6 will just be 3x squared over x cubed plus 6 quantity squared. That's y prime. There's my answer. Now, should you simplify? Yeah, if you can. A lot of times these are super messy and it's not worth the hassle, so I'm fine. Let's leave it like this. If you can simplify the numerator quickly and there's something that's like going to make this reduce down quite a bit, then go ahead and do it. I just don't, I mean, we could expand these, right? We could do all this distribution and combine like terms, but I don't think it's going to make this look that much nicer. And we've technically done all the calculus, so this is the derivative. It's just a big messy function. All right. No, and in fact, you would almost never want to expand the bottom. The whole point of expanding the numerator is in hopes that you end up with a factor of like x cubed plus 6 left over that you can like try and divide out from the bottom. So you would want to keep that denominator in factored form. But simplifying is such a gray area, right? Like, yeah, you want to if you can, and if it's going to make things look nicer. But if it's just going to make things look equally messy, it's really not worth your time. And this is calculus. This isn't algebra 1. So I trust that you guys know how to multiply out and simplify if you need to. All right. So here's just a quick word of wisdom about the quotient rule. Don't just, and I said this about the product rule too, don't just immediately default to, I have to use the quotient rule here. If you can simplify at first and avoid it, that's good, because as we can see, the quotient rule is a little bit messy to use. So something like this. Yeah, it's a quotient, but the denominator is just a monomial. It's just x. So I could technically rewrite this as 3x squared over x plus 2 root x over x. Now this is technically x to the first power in both cases. This, oh, come on. I just accidentally closed my... Now the, okay, so I had 3x squared over x plus 2 root x. What I was about to do was rewrite root x as x to the 1/2 over x. And these are technically x to the first power. What can I do to simplify a quotient of powers? What can I do with the exponents to simplify a quotient of powers? Help me out with that. Yeah, you would subtract. In which direction? Top minus bottom or bottom? Yeah, top minus bottom. So this then becomes 3x plus 2x to the negative 1/2, because 1/2 minus 1 is negative 1/2. And there. Now this is much easier to differentiate. You don't have to use the quotient rule, right? You can just use the power rule. F prime just becomes 3 plus, or I guess it would be negative 1/2 times 2 times x to the negative 3/2, which is just 3 minus x to the negative 3/2. And boom, we've avoided using the quotient rule. Now, would the quotient rule work? Of course. You could use the quotient rule in this. It would absolutely work. It would just be a lot messier and take a lot more time probably. And it has a lot more steps. A lot more steps means there's a lot more opportunity to make some sort of a small clerical error. Does that make sense? Okay, so this is just a reminder of that. What rule, right off the bat, could I use to differentiate this? Let me give you a hint. This is root t times meaning a product. What rule could I use to differentiate this? We gotta get you. Thank you for humoring me. We gotta get your guys' typing speed up here. There's too much lag. Yeah, you could use the product rule. You don't need to though, because we could rewrite this as f of t equals t to the 1/2 times a plus b times t. Then I could distribute that t to the 1/2. And I can have f of t equals a t to the 1/2 plus b t to the, what do you do with the exponents when you have a product of powers? Add. What's 1/2 plus 1? Don't say 1.5. 3/2. Excellent. And now we can take the derivative, avoiding using the product rule. Remember that a and b in this case are just constants. T is our variable. So I'd have 1/2 at to the -1/2 plus 3/2 bt to the +1/2, and there's my derivative. All right, now that being said, sometimes the product or the quotient rule are unavoidable, or they're just easier to use, and then in which case use them. Just be on the lookout for, can I simplify this quickly and easily before I do calculus to it? Let me just see. Oh, this is our last example. All right, find the equations of the tangent line and normal line to the curve y equals √x over 1 plus x squared. So this is a great example where there's not really anything you can do to simplify it. And we're just going to go ahead with the quotient rule. First thing I do if I have a function that has a radical in it before I do any calculus to it, we're going to rewrite that radical as an exponent. Right? So √x just becomes x to the 1/2. Now, because the quotient rule is messy, I'm going to do it in 2 steps. So I'm going to use my differentiation operator. So here we go. We're going to go y prime, oh, come on. Y prime equals. So we're going to go low d high, so low 1 plus x squared times derivative of high, so the derivative of the top is the derivative of x to the 1/2 minus high d low, so minus x to the 1/2 times derivative of 1 plus x squared. Low d high minus high d low, square the bottom, and away we go. Cool, so we're all set up to do the calculus part. We just haven't done it yet. We just need to do the calculus on these 2 parts. All right, so 1 plus x squared times the derivative of x to the 1/2 will be 1/2 x to the -1/2 minus x to the 1/2 times the derivative of 1 plus x squared will just be 2x. All right. So that's my derivative. My derivative we're going to use to find the equations of first the tangent line and the normal line to the curve that we were given at the point 1, 1/2. So we always need 2 things to write the equation of a line, a point and a slope. We have the point. What is the derivative going to help us find? What is a derivative? Geometrically, what's a derivative? There we go, slope. So the derivative is going to give us the slope, right? So this is a case where you certainly don't want to simplify, because all we're going to do is plug in 1 for x. So there's no reason to try and simplify all these x's when we're just going to be replacing all the x's with constants, and it's much easier to just do order of operations and simplify constants down than it is to like deal with variables and combining like terms and stuff like that. So I'm not going to do anything. I'm just plugging in 1 for all the x's. So I have 1 plus 1 squared times 1/2 times 1 to the negative 1/2 minus 1 to the 1/2 times 2 times 1 all over 1 plus 1 squared quantity squared. And this may seem messy, but we're doing just a bunch of this stuff to ones, and ones are pretty easy to simplify, right? Oh, God damn it. No. I just deleted that whole thing on accident again. All right, that'll probably give you guys a chance to catch up. Oh, God. Minus. All right, and we said y prime at 1. All right, I'm going to start simplifying from that last step. So that gives me 2 times 1/2. Because 1 to any power is still 1. So 1 to the negative 1/2 is still 1, right? Minus, plugging in 1 there, I get minus 2 over 4. 1 minus 2 over 4, that's negative 1/4. All right. The derivative is the slope of the tangent line, right? So my tangent equation will be y minus 1/2 equals negative 1/4 times x minus 1. How does the normal line relate to the tangent line? How does the normal line relate to the tangent line? We talked about this, right? Normal force. You guys better just be typing really slow. How does the normal line refer to the tangent line? Or how does it relate? Oh, yeah, perpendicular. So how do I get a perpendicular slope? I know the tangent slope was negative 1/4, so what will the normal slope be? Good, it's opposite reciprocal. Opposite in sign, reciprocal. So flip it and change the sign. So if the tangent line has a slope of negative 1/4, the normal line will have a slope of positive 4. Now you will still want the normal line going through that point of tangency. So our equation just becomes y minus 1/2 equals 4 times x minus 1. The only thing that changes about that note is the slopes are opposite reciprocals of one another. They'll go through that same point of tangency on the graph. And that's it.